Okay, now we can take the results that we've obtained for these different components of the momentum balance and substitute them in. So remember, I labeled this equation star star, the momentum balance, and I'm writing it down here again. Sum of the forces, and again we're looking at the x component. The x direction we defined as being along the axis of the pipe, or along the flow direction through the pipe, minus m dot dv equals 0. So we looked at different kinds of forces. We looked at the pressure force, so the net pressure force acting on this system minus the cross-sectional area times dp. The net gravity force, dF sub g, equal to minus rho g times the cross-sectional area times dz prime, where z prime represents the vertical direction. The net force due to wall drag is minus the wall shear stress times the perimeter, the wetted perimeter, times dx. And any contributions due to shaft work within this system. So that force is equal to minus delta W times dx, right? The work divided by the displacement associated with the with this way we define the control volume. So we plug all these into the sum of the forces in the momentum balance, and we get the following result. I have minus ax delta p, the pressure force, minus rho g ax dz prime, the gravity force, minus tau wall times the wetted perimeter times dx, plus delta ws over dx minus m dot dvx equals 0. So now we can simplify this sum. So first thing we're going to do is divide by rho ax. So the density times the cross-sectional area, minus rho ax. And we'll do that here on the next slide. So we get dp over rho plus g dz prime plus tau wall times the wetted perimeter times dx over rho ax plus this shaft work term divided by rho ax dx plus m dot over rho ax times dvx equals 0. Okay, notice that ax, the cross-sectional area, times the length dx of this disc-shaped volume, that's equal to the volume of our system. So rho times the volume, this is what we have in the denominator here. So mass per unit volume times volume is just mass. So this term represents an expression of work per unit mass. So I'm going to write that in the shorthand term, delta ws, where this is a lowercase w. This is an uppercase w. So lowercase w means work per unit mass. And remember that the mass flow rate, again, is rho va. And since we're just talking about the x component here, we have rho times the x component of the velocity times the cross-sectional area. Okay, so now we can substitute these again into the equation for the momentum balance and simplify it further. So I have dp over rho plus g dz prime plus tau wall times the wetted perimeter over rho ax times dx plus the shaft work term delta ws plus vx dvx. And then all that equals to 0. So I can integrate this now from the inlet to the outlet of the pipe. So along the x direction. So if I do that, I have the following. So I have the integral from inlet to outlet of dp over rho plus g times z prime at the outlet minus z prime at the inlet, the change in height, plus integral from 0 to L of this wall shear stress or wall drag term, tau wall wp over rho ax, plus the work term, plus this term, right? So the integral of v dv is 1/2 v squared. So we have 1/2 vx at the outlet squared minus vx at the inlet squared. Then I'm going to assume that we have incompressible flow, so the density is constant. We can take that out of all the terms where it appears in an integral. And when we do that and integrate from inlet to outlet, then we get the following. And I'm rearranging it a little bit. You'll see why in a minute. So I have p outlet minus p inlet over rho plus 1/2 v outlet squared minus v inlet squared plus g times z prime out minus z prime in plus the integral over the length from inlet to outlet of this wall drag term, tau wall times the wetted perimeter over rho times the cross-sectional area, plus this work term equals 0. Okay, does this look familiar? It should, actually. It should look very familiar, especially if you compare these first three terms with what we saw in Bernoulli's equation. So let me write that again here. So remember, Bernoulli's equation, as we're seeking to apply it to pipe flow, looks like this. Delta P over rho plus the kinetic energy term, which we express in terms of the correction factor and the average velocity, so alpha delta V average squared over 2, plus the potential energy G delta Z, and then we added these two terms, the viscous loss term and the shaft work term, and so those equal to 0. So these equations would actually be identical when this viscous loss term is equal to this term in the momentum balance that represents the wall drag. And so, right, if L sub V is equal to this integral of the wall shear stress times the perimeter over rho times the cross-sectional area dx. So this actually makes perfect sense, because this is what we said all along. We said that these viscous losses have to be related to effects that are taking place at the wall, where we have the highest velocity gradients, because Bernoulli's equation, as we originally derived it, is only valid in the bulk flow, away from walls, because the wall region is where these viscous effects are localized as a result of the velocity gradients that appear there. So this exactly matches what we expected. So we're able to get at this, what the form of this term should look like, by considering the macroscopic conservation of momentum. So this gives us a clue about the form that we need to apply to express these viscous losses in terms of Bernoulli's equation, right? And these losses are related to viscous friction effects through this wall drag term. Okay, so the next issue becomes, how do we get an expression for this wall shear stress term, tau wall? Well, we already know how to do that, because if you remember back in the early videos where we talked about the definition of viscosity, we looked at the constitutive relationship, and we looked at Newton's law of viscosity as a specific relationship that connects stresses to rates of deformation, or stresses to velocity gradients in the fluid, and those are connected by this viscosity coefficient, which for a Newtonian fluid is mu, a constant. So the wall shear stress is just related to the velocity gradient at the wall, evaluated at the wall. Okay, so for pipe flow at steady state, then this actually simplifies quite a bit, because we know that these terms are constant at steady state, right? We solved the Navier-Stokes equations, we get a steady state velocity profile, and then we can take the derivative of that and evaluate at the wall to get the wall shear stress, and that's a quantity that's constant over the length of the pipe. So this comes out of the integral, and we basically just have the integral of 0 to L of dx, which is just L. So our viscous loss term is just this quantity tau wall, the wall shear stress, which we can get from the velocity gradients at the wall, so that's known, or can be obtained, times the perimeter, divided by the density times the cross-sectional area times the length of the pipe. Okay, so and that's basically the result. But for convenience, we can write that in a slightly different way. So I'm going to take this tau wall over rho term, break that out, and then multiply it by this other term, 4L over d sub h. So what is this d sub h? D sub h is a parameter called the hydraulic diameter, and it's basically a shape factor. So this incorporates the geometric parameters in the problem. So we have cross-sectional area and the perimeter. So this hydraulic diameter is 4 times the cross-sectional area divided by the wetted perimeter. And so we just basically substituted this, dh over 4 for this ratio ax over wp. So this is basically a shape factor. So this is important because it allows us to consider any pipe shape. It doesn't have to be a circular pipe. It can be, but it doesn't have to be. As long as we know what the cross-sectional area is and its perimeter, then we can determine the viscous losses for that. So it's not specific to a particular shape or geometry of the pipe. So that's important consideration. Now, by convention, often we define what's called a loss coefficient. So instead of dealing with this term directly, this viscous loss term directly, it's convenient to express it in terms of a dimensionless quantity because, again, remember, dimensionless quantities allow us to get more general expressions so we can see broader trends and then make them specific to the problem that we want to consider by converting them back to dimensional form later. So we're going to define this loss coefficient as the ratio of the energy dissipation due to viscous losses, L sub v, relative to the kinetic energy associated with the flow, 1/2 v squared. Okay, so this definition for the friction factor K is totally general. Remember, it's just a dimensionless ratio between the viscous losses relative to a characteristic energy scale of the flow, which we take to be the kinetic energy, 1/2 v squared. So it's customary to take this general definition and specialize it for the case of pipe flow by recognizing that the viscous loss term, remember, involves this quantity associated with the wall shear stress, tau wall over rho, times other quantities that are just basically related to geometry, involving the length and the hydraulic diameter. So it's customary just to break out this wall drag component and express that relative to the average kinetic energy of the flow. So this quantity, tau wall over rho over v squared over 2, is a specific representation of the viscous energy dissipation relative to the kinetic energy of the flow for pipe flow problems. And this parameter is given a special symbol, lowercase f, and it's called the fanning friction factor. So we can see the relationship between these friction factors if we look again at the definition for this viscous loss term that we obtained on the last slide. So remember, it's the wall shear stress, tau wall over rho, times this geometric term, 4L over the hydraulic diameter. And so our definition for the loss coefficient, our general definition, is LV over 1/2 v squared. So basically we take this collection of terms and divide it by 1/2 v squared. And so notice then that these collection of terms that I've circled in red is equal to this fanning friction factor F, which we defined as being a collection of terms or a ratio that is specifically relevant for pipe flow. So we've separated out basically the terms here that depend only on the geometry of the pipe. And so therefore, the relationship between these two friction factors is as follows. The general friction factor K is related to the fanning friction factor F by as follows. K is equal to 4FL over the hydraulic diameter. Okay, so now we have a way, using these friction factors, to express viscous losses in a pipe. And so that allows us then to apply Bernoulli's equation to solve pipe flow problems.